Eric Reis was 20 years old. He was a web designer in a small town in southeastern Brazil, and on that particular afternoon in February 2013, he had just finished filming an engagement party for some friends. He was walking to his car in the late afternoon sun when he looked up and stopped. The sky above him was filled with spiders, thousands of them, suspended in the air, drifting slowly against the light, some of them appearing to descend toward the ground. He pulled out his camera and started recording. That video, shaky and bewildered, would go on to accumulate more than 2 million views on YouTube within a week and make the small town of Santo Antonio da Platina, Brazil, internationally famous for the worst possible reason. It was raining spiders. The footage is surreal. Against a pale blue sky, you can see dark specks everywhere, hundreds of tiny shapes hanging at different heights, some motionless, some crawling, others appearing to float downward, as if gravity were gently lowering them to the streets below. Power lines and telephone poles are draped in what looks like a fine, silvery fabric. If you did not know what you were looking at, you might think it was some kind of strange atmospheric debris. But it was not debris. It was silk, and every dark speck moving against that silk was alive. The people of Santo Antonio da Platina had never seen anything like it. Neither had most of the world. The video spread across international news within days. Headlines called it spider rain. Social media treated it as a horror movie come to life. But for biologists who study arachnid behavior, the footage was not a nightmare. It was a textbook example of something they had known about for years, but rarely seen captured so clearly on video. What happened in Santo Antonio da Platina was not weather, it was biology. And to understand it, you need to know what kind of spider was in that sky. The species responsible was identified by Marta Fischer, a spider biologist at the Pontifical Catholic University of Paraná. She confirmed that the spiders belonged to either Parawixia bistriata or Ankylosamus eximius, both classified as social spiders. That distinction matters because out of the roughly 40,000 known spider species on Earth, only about 24 are social. The vast majority of spiders are solitary hunters. They build their own webs, catch their own food, and avoid other spiders entirely. Social spiders do the opposite. They live in colonies that can number in the hundreds or even thousands. Parawixia bistriata is native to tropical and subtropical regions of South America. During the day, these spiders cluster together in a communal resting spot, usually a tree or a dense bush, huddled in a tight mass called a bivouac. At sunset, they emerge and begin building. Each spider constructs its own individual web, but all of those webs are anchored to a shared scaffolding of thick support lines that the colony builds together between trees, poles, and other structures. The result is a massive communal web system that can stretch across enormous distances, sometimes spanning 20 meters or more from the ground to the treetops. The webs are designed to intercept flying insects, and the communal approach dramatically increases the amount of prey the colony can catch compared to any individual spider working alone. The silk they produce is remarkably thin. In the right light, the threads are visible as a glistening silver sheet, but under overcast skies or at certain angles, the supporting threads become nearly invisible to the naked eye. This is the key to the illusion. When the spiders are active in their webs and the threads cannot be seen, it looks exactly like the spiders are floating in midair. Add a light breeze that causes the web to sway and the spiders to shift position, and it appears as though they are drifting downward from the sky. It looks like rain. But the illusion goes further than that. If a strong wind hits the web system at the right angle and with enough force, sections of the communal web can detach from their anchor points entirely. When this happens, the wind carries the web, along with every spider still clinging to it, away from the colony and into the open air. The spiders are not choosing to fly. They are being carried. Their home has been ripped loose and is sailing on the wind like a giant, invisible net loaded with passengers. When the wind drops or the web catches on new structures like power lines or rooftops, the spiders settle wherever they land. And to anyone standing below, watching dark shapes descend from above, it looks like spiders are falling from the sky. This is almost certainly what happened in Santo Antonio da Platina in February 2013. The colony had been living in nearby trees, building their communal web system as they do every evening. A gust of wind, likely associated with a late afternoon weather shift, tore sections of the web free. The wind carried the silk and the spiders over the town, where they settled on power lines, telephone poles, and rooftops. Eric Rice walked outside at exactly the right moment and captured the aftermath on camera. But the story of airborne spiders does not begin or end in Brazil. Spiders have been traveling through the air for as long as there have been spiders, and they have been doing it in ways that scientists are still trying to fully understand. The phenomenon is called ballooning. A spider, usually a small one or a newly hatched spiderling, climbs to the highest point it can find, raises its abdomen toward the sky, and releases one or more threads of silk into the air. The silk catches the wind and lifts the spider off its perch, carrying it into the atmosphere. Some spiders travel only a few meters, others have been carried extraordinary distances. Spiders have been found 4 kilometers above the Earth's surface. They have been documented landing on ships hundreds of miles from the nearest shore. Charles Darwin himself observed hundreds of ballooning spiders landing on the HMS Beagle while it was sailing far out at sea on a calm day in 1832. He watched them take off again from the rigging of the ship and vanish into the sky on a day with almost no wind, which puzzled him deeply. For nearly 2 centuries, the accepted explanation was simple aerodynamics. Light wind catches the silk thread, creates drag, and lifts the spider into the air. But that explanation never fully added up. Ballooning has been observed on windless days, under overcast skies, and even in light rain. Spiders much too large for wind alone to lift have been documented ballooning successfully. And the fan-shaped pattern that some spiders produce with their silk strands, splaying them out in multiple directions rather than letting them trail behind, did not match what aerodynamic drag alone would predict. In 2018, a team of researchers at the University of Bristol, led by Dr. Erica Morley, published a study in the journal Current Biology that offered a new explanation. They found that spiders can detect and respond to the Earth's atmospheric electric field, a naturally occurring vertical electric gradient that exists between the ground and the upper atmosphere. When Morley's team exposed spiders to electric fields equivalent to those found in nature, the spiders began performing ballooning behaviors, raising their abdomens and releasing silk. When the field was switched on, the spiders rose into the air. When it was switched off, they sank. No wind was involved. The spiders were being lifted by electrostatic force alone. The silk itself, carrying a slight negative charge, was being repelled upward by the negatively charged ground surface and attracted toward the more positively charged upper atmosphere. The spider's tiny sensory hairs, called trichobothria, were shown to be mechanically sensitive to these electric fields, meaning the spiders can literally feel when atmospheric conditions are right for flight. This discovery did not replace the wind-based explanation. It added to it. Ballooning, it turns out, is likely powered by a combination of aerodynamic drag and electrostatic lift, with the balance depending on conditions. This means that spiders are not just passively caught by the wind. They are active participants in their own flight. They choose when to launch. They can sense the electrical state of the atmosphere. And they have been doing this for hundreds of millions of years, long before any bird or insect took to the sky. The event in Santo Antonio da Platina was not ballooning in the traditional sense. Those spiders were not launching themselves individually. They were being carried as a group on a broken web. But the underlying principle is the same. Spiders in the air have a relationship that most people never think about until they look up and see something that should not be there. Animal rain in its various forms has been documented for thousands of years. Fish have fallen on towns in Honduras, Louisiana, and Australia. Frogs have rained on Serbia, Belgium, and Kansas City. Worms have dropped on Louisiana and Norway. But spider rain occupies a unique place in that catalog because, unlike most animal rains, it has a clear and well-understood biological explanation. There is no mystery about where the spiders came from or how they got into the air. The mystery, if there is one, is how long it took science to fully understand what spiders have known all along. That the sky is not off limits. It never was. For a creature with silk and the right instincts, the atmosphere is just another place to travel. Santo Antonio da Platina returned to normal within a day. The webs broke down. The spiders dispersed into nearby vegetation. Eric Rice went back to designing websites. But his video remains one of the most viewed pieces of footage of animal rain ever recorded, a 60-second window into a world where the line between the ground and the sky is thinner than most people realize. The spiders in that footage were not invading. They were not falling. They were just passing through. And for anyone who happened to be standing below at that particular moment in that particular town, it was a reminder that nature does not always follow the rules we expect it to. Sometimes it rewrites them entirely,